So always V2 equals 0. And they are completely elastic. Kinetic energy is conserved. This word completely is not necessary. I always add it in my mind. I'm going to have one object M1, which I bang against object M2, and object M2 will be standing here, will have no speed. And object M1 comes in from this side, and I'll try to make the collision elastic. And the way I will do that is by using springs, which are attached to each mass. And springs are conservative forces. So there is almost no heat that is generated in the springs during the collision. And so to a reasonable approximation, you will get an elastic collision. But of course there's always air drag. I can never take air drag out. So there's always some external force on the system. So momentum is never exactly conserved, and kinetic energy is never exactly conserved either. So it's only an approximation. So I have one mass of unit 1. I will tell you what that is. And I bang that into number 2. And the masses that I have, one mass is 241 plus or minus 1 gram. And the other mass that I have is 482 plus or minus 1 gram. And I have 2 of these. And in my first experiment, I will use these 2. So this is the ratio that you see, 1 to 1. I will give it a certain velocity, which I cannot tell you what that is. That depends on how happy I feel. If I push hard, then the velocity will be high. If I push softly, the velocity will be low. But it is something. And then we're going to get here V1 prime. And there is a prediction that this velocity will be 0. Look all the way on the blackboard there. You will see if the masses are the same and there's an elastic collision, this one will stand still, and this one, V2 prime, will have a velocity V1. So that's a prediction. The second case, I bounce one car onto another one which is twice the mass, certain velocity, which I don't know what it is. And now, what are we going to get? So mass M1 is half the mass of M2. So this is a 1, and this is a 2, and this is 3. 1 minus 2 is minus 1, divided by 3 is minus 1/3. So number 1 comes back. No surprise. If you bounce a lighter object off a more massive object, no surprise that it bounces back. So that's minus 1/3. And when we look here, we have 2 times 1 divided by 1 plus 2 is 3. That is plus 2/3. So number 1 will come back with a speed 1/3, which of course, since this is sign sensitive, we get 1/3 V1. And this one is plus 2/3 V1. That's the prediction. And the way we're going to measure it is by measure the time for the objects to move over a distance of 10 centimeters. No matter how long you see these cars to be, there is here a piece of metal which is 10 centimeters long. It goes through a slot with a diode. We have one system here and one there. And during this 10 centimeter movement, we measure the time. We begin when this piece of metal enters the diode system, and we stop the time when it leaves the diode system. And each one of those cars has this 10 centimeter metal plate. So the way we're going to do this is by measure timing, of course. This velocity will give me a certain time, and this velocity will give me a certain time. Whatever comes out, you will see that on this timer. Then T1 prime is, in this case, it stands still, so must be 0. And T2 prime must be the same as T1. So these two numbers you should be able to compare directly. What kind of uncertainties do we have? It's hard to tell. But I would say, as I argued last time, that you should allow for at least about 2.5% uncertainty in each time. If it comes out better, then you're lucky. If it comes out worse, then it is a bad day. 2.5%, and I argued last time how I reasoned about the 2.5%. Now we do this experiment, we get a certain t1. And so this one goes back with 1/3 of the speed, so it will take 3 times longer to go 10 centimeters. So I'm going to multiply this time by 1/3, and whatever comes out should be the same as this. So let me move this up a little. T2 prime. The speed here, the forward speed, is 2/3, so it will go slower. So if I multiply this time by 2/3, then I should be able to compare it with T1. And all of that, all these times, I think, will not be any better than roughly 2.5%, except if we are a little lucky. Okay, system is up, timers are up, timers are up. This will be the time T1. This will be the time T2 prime. And this is the one when the object bounces back. So this is T1 prime. You won't see that it is negative. It will go back through the same slot. And the electronics is arranged in such a way that when it goes back through the same slot, that it will initiate this timer. I will zero them. First you have to tell me whether they are working. I will just let it go through this slot. This one working. Tell me that this one is working. If I send this one back, this one working? Okay. Okay. There we go. This is the one that will have no speed, and this is the one that we're going to give a velocity. You ready? I hope you know what you're going to see. This one will come to a halt, and this one will go on. They have same mass. There we go. This one is indeed coming to a halt, and this one took over the speed. What are the numbers? 194 and 196. Only 2 milliseconds difference. That is an incredible result. 0.194 and 0.196. It's only 1% difference between them. Way within my wildest expectations. Because my expectations were that they could be off each by 2.5%. Now we go to the 1 to 2. So here is the car which has twice the mass. It's important that I zero it. And now this one is going to come back. So you're going to see this one come in, give you the time here. This one goes through here, gives you the time here. This one will come back, gives you the time here. Are they zero? Okay. You ready? Yeah. There we go. Okay. Now comes the real acid test. 1, 2, 3, 1, 8, 6. 1, 2, 3. And what is the last one? 3, 7, 5. Okay, let me be lazy. And let me use my calculator. 375 divided by 3. I could have done that by heart, of course. This is 0.125. An amazing agreement. Amazing. Only 2% off, less than 2%. Now here, 0.186 times 2 divided by 3, 0.124. I can't believe it. Less than 1% off. So you see in front of your eyes that we were able to create something that was indeed extremely close to elastic collisions, in spite of all the problems that we have air drag, and that, of course, there is always some loss of kinetic energy.